Hello, ladies and gentlemen, and welcome to the lab assignment, the lab practical for GGS300 for the first lecture. So today I'm going to walk you through some of the analysis which we're going to do in R. So basically it's an introductory session where we'll go through how to use the software, how to use the virtual laboratory, and potentially how to install the software on your own computer if that's what you would like to do. So just before I begin, I'm just going to try to get you all up to speed with using the software that's available. So GMU has the ability for you to access the virtual laboratory software, but you need to install quite a few applications in order to make this work. So firstly, if you've not accessed the VPN, so the virtual private network, then you will need to download Cisco AnyConnect, and I've provided you with the link here, and essentially you'll need to go on there, download the software, and you can follow the installation instructions which they provide. You'll be able to install the correct version for the platform, the operating system that you're using, and then you will need to understand how to log on to the VPN, which will require you to enter some of your IT login information and have two-factor authorization set up. Then also you'll need to download Citrix and install it. So I provided you also with the link here on how to do that in case you don't know already. So you need to follow the installation instructions, which will actually include downloading it first. I'm going to circulate to you a PDF which contains how to do all of this, so you can follow the instructions there, and then once you've done that, you can essentially log into the virtual lab. Here are the instructions which I will circulate to you for you to access. So I'll circulate those in due course. And then once all of it's installed, you basically connect to Cisco AnyConnect, and then you connect onto Citrix. Now I've loaded the virtual laboratory and I've played around with the software on there, and it's fine, but there's a bit of latency on my system. So what you may want to do is to install R yourself on your own system. So bear with me while I just try to get this set up. So this is logging into the virtual laboratory. So you saw once I had Citrix installed, I went to the Citrix receiver, then I can click on Mason Lab and I can open this up. So I'll just give you a bit of an overview of what you need to do on there. So there will be code and data which you need to download. So that's me logging into Citrix now, into the virtual laboratory. As you can see, it takes a little bit of time on my machine. I'm not sure if it's going to be the same on yours, but definitely I'm having to access the server, no doubt, and having to go across the Atlantic submarine cables. So that's causing a little bit of a delay. And then once you're in, what we want to do is you want to access RStudio. So you can either just type like I did there, or you can scroll to it, but you want to find the RStudio application. So as I said before, you'll need to download the code and the data for this lab from the Blackboard site. And essentially you'll need to put all of that information to a single folder which you're working from. And then you'll need to open up the R software. As I mentioned before, it's fine if you use it here, but you can also install it on your own machine. So I'm going to exit this now, disconnect. So I've shown you how to log in essentially and how to get it started. But just for the sake of mitigating the latency which is present, I'm actually just going to show you how to also install it on your own machine. And also I'm going to work on my version so that you aren't subjected to the delay during the class. So I've covered this already for how to set up. But the alternative option is that you just download a version of RStudio directly onto your machine. And this is one of the great things about open source. When I started in this area 10, 15 years ago, we would have to use Minitab or SPSS or some other sort of proprietary software, and we generally have to either buy a license to use on our own machine, or would have to go into the computer labs at university or college, and that was just generally annoying. So I did move about 6 or 7 years ago onto R because it was open source. So that was one of the great things. So I'm glad that you don't have to put up with some of the frustrations which I always had around needing to get a license and then renew your license annually once the previous one had expired. So you can just follow the link which I provided, and it takes you through to the RStudio website. The beauty of downloading RStudio is that it will download both R, which is the programming language, the statistical language, and then the RStudio part, which is basically the integrated development environment. So it's this bit here, the IDE, which sits on top of R and makes it easier for you to do things because it provides a graphical user interface. So I will show you what I mean by this later on. But essentially, if you go down here, you don't want the server version, you want the desktop version. So you're just a single installer. And when you click on the desktop version, it will take you down to the open source edition. So down here, you just click download RStudio Desktop. And then it will say, choose your version. And you want to be over here on the free version, so you can just download it. And then when you get down here, it probably will pick the version that it thinks is best for your operating system. So it's suggesting a version here for me. If you're on Mac or you're on Linux, then it will suggest something different. But essentially, you're then able to download that, and it should be fairly easy to install. Just follow the install instructions. And then hopefully you'll be able to access RStudio like I'm doing here. There we go. RStudio is already installed on my machine. So download the lab code from the Blackboard, save it into a working directory, open R, and then navigate in the File tab to open the files. So I have all of my code, so this item here and the data saved within this folder. And just for the sake of showing you how to do it, you can open a file. So you can either go to the File menu and click Open File, or you can just click this yellow button here. And then when you go in, so I'm going to go into where my folder is located, which is here, Lab 1. And you will want the lab1.r script. So it did actually show as a PDF there, and that's just an issue on my machine. So hopefully you won't have that. It will probably show as an R script, but that will give you the code essentially to open up what we need to use in this session. So this is the R graphical user environment. Don't be scared by what's here. Essentially what we have is a console. So this is where you're able to write code and have the machine process that information using the R syntax. So if we just type hello world, which is the fairly standard thing that people first write when they start to learn programming. It's the first thing that was first written on a computer 5 or 6 decades ago. So that's a fairly standard thing for people to type into the console, and you can see that we've written it and it's just returned it. So you're also able to essentially create a variable out of this information. So you could say x equals hello world. There we go, and now we've stored this variable which is equal to hello world in the memory of the program. You'll see it shows up here in the right hand side. So this is our environment, which contains all of our variables and data. And then within the console here, we can then type x, and it will essentially print to the console what x is, and x is equal to hello world, as we essentially showed before. So you can write things directly in the console. So 2 + 2 = 4 as an example. But the way that we're going to be using the program is by using an R script. And then the R script is able to trigger the code that you want to run. This is a fantastic thing, because if you're used to, for example, to using an ArcMap or Excel, generally you have to carry out the processing that you want to on spatial data or any just normal type of data. You have to carry it out manually, and you have to go through each step. Whereas here we're able to be explicit about what the steps are, and then we're able to just, at the click of a button, once we've written the code, rerun all of the processing steps. And that means that you're able to do reproducible research, and that's a fantastic thing. And it also saves so much time. So for example, I learned the hard way, which was when I first started submitting academic papers, you would do a lot of work, submit it for review, and they would come back and say, no, you need to change all of these things. And if you haven't basically used a script to program everything that, all of the processing steps that you produced, then you might have to manually reproduce all of those steps, and that's incredibly arduous. So the beauty here is that this is very easy to repeat the analysis with the click of a button. So here what we've got is a script. And in this script, we're able to write. So here's the text that we're able to write in. I think the first thing that I want to say is that by using a hash or a £sign like this, that means that we're able to write text which isn't executable. So not. Right, so now if I was to run this text, it doesn't actually process that. So if we go 2 + 2 here, and we run this line, we get 4. But if I was to put 2 + 2 up here and run it, you see the £sign is still in front of it, so it doesn't actually process it. So it just treats this as text, essentially. Whereas this down here is actually treated as something which can be processed as numerical information, so it actually produces the number of interest. So that's essentially how we've got all of this written text here, and it won't be processed because it's got a £sign in front of it. And then the other thing that I should point out is that when you write something in here, as I just did, for example, 2 + 2, you want to be able to run that code. I was just using the hotkeys before, but you will want to either run it here. So you just click the run button, and you see 2 + 2 was printed to the console just here. But you could also use the hotkey, so you can either highlight the text and press Control-Enter. I know you can't see me doing that, but if you press Control-Enter here, then you'll be able to reproduce that. Or if you just have the cursor on that line, you press Control-Enter, it will also just run that single line. So that's essentially how you actually trigger some analysis. And I think we've already been through basically all of this here. So we've created the folder that we've opened this script in. We've downloaded the data, it's in the right place, and we've opened our studio. We may want to know about which working directory we're in. So if we go get wd, that tells us that we're in this working directory here. So C users Edward, and that's the current working directory. We may also want to set the working directory, which essentially you would need to input an actual file path to set the working directory, which you can do here, and you can do that manually or automatically. If all of the data and the code are in the same folder, then you should just be able to run everything in the same place. Hopefully you won't have any issues there. I think one of the other things before we begin, and I'm thinking about this now that we've got to the part where we're using commands that we maybe don't know how to use, and there might be some issues with how we resolve those errors. Essentially, there's a question around, well, what do you do when you get stuck with a piece of code within the R program, for example? I will circulate information on decent R documentation that you might want to read, but it can be quite dry, and the benefit of actually just Googling the problem that you have, or the error message that you have, is that usually someone will have had the issue before, this is one of the key ways in which we debug our code, the way that we resolve issues that we have when we're carrying out statistical analyses. So if in doubt, Google the problem and see if online there are forums or Stack Overflow questions where people have answered them and basically explained what to do in this situation. So for example, check out Stack Overflow, as I mentioned before. It's this fantastic resource. So it's a big forum where there are thousands of questions. You can search your question in here, essentially people will provide you with suggested answers to the problems that you have. So you do need to know how to ask a proper question though, and that's why I've provided you with this link here. I use Stack Overflow maybe 3 or 4 times a day. I use it all the time to find code that I need or to solve problems that I have. But you shouldn't be asking a question each time. You should be looking at the existing questions and using the existing answers to those questions. And if you were, say, to post a question and not write it in the right way, or you were to post a question and it be a repeated question, then the community on here, which is very large and global, will probably give you a negative feedback rating for your profile. So they do have the ability to do that. Sometimes they can be quite cold about the matter. So I would advise you to read up on how to ask a good question on Stack Overflow, because particularly when you're on the homework or you're doing your dissertation research later, this may be invaluable for you for how you solve coding issues. So please look in here. I also just want to say that you should really be producing a reproducible example of the problem that you have. So for example, I've covered all of these first 3 points here, but this fourth one here, if you just say, I have this error message, that's not really very useful, and it's very hard to debug that. But if you provide a small example of data, and then you provide the code which you're analyzing that data with, and then you show the output, then someone will probably come along and say, okay, right, this is the issue with your code. And that's why I'm saying you need to produce a reproducible example so that people are actually able to help and debug and see what's going on. So this is pretty important. So we've talked about how to get the code in the right place. We've talked about setting the directories. We talked about how to resolve issues that you might have using either Google or Stack Overflow. So I think we're about ready to move on now. We've also covered this. So our commands, they have different types of components, and you can do a lot of different things. You know, any type of mathematical operation that you want to do, there's probably a way to do it within R, and there are thousands of statistical packages that people have produced to do all manner of analyses. What we're doing here is fairly simple, and I'm just introducing you to the basics of it. But it's definitely worth taking a look at some of those packages. I mean, the nice thing also about R is that if there, for example, was something that wasn't covered, then someone would probably write the package for you, which is very nice. So, okay, what I'd like you to do on your own machine when you go back over this code is to actually run and understand what's going on here. So I know I already showed you that you could essentially write mathematical operations or functions here, and that it would be processed, and then the output would be printed to the console. But this text here just provides you with a bit more of an understanding about what's going on. As I mentioned before as well, you can actually assign anything that you would like to a variable name. So here we're just treating the variable name as x, and you can see that like I did before, we've stored it in the RAM, so in the memory of the program, and then we're able to just run x to obtain the actual answer to the mathematical expression that we previously provided, and that's printed out to the console. So you'll have seen that I used both an equals sign, and also you can assign to a variable. So I essentially did this before. So x equals 2 plus 2. And when I run that and run the 2, we get 4. Great. You can also do x assigned 2 plus 2, like this, and then when we print x, we also get the same. We get the same output. So there's often many different ways to do the same thing within pretty much any programming language. There's often many ways, and the reason why you might choose one or the other is either the functional ability or the speed or efficiency, but generally you can use whichever assignment operator you would like here. I started using the arrow. It is an extra key to tap if you're worried about that. Having programmed in other languages now, I much prefer the equals sign, but I'll leave that decision up to you. I'll be agnostic in the marking of the work, providing that you're producing well-written code which meets the objective and produces the answer which we're looking for. So that's the assignment operator, and technically it also works in the opposite direction, but I personally don't use this, and I've never used it like this before, so I wouldn't advise you to. I mean, the reason why is partly also because there are formatting standards to how we write code, and normally that means that you would start with the function or the variable name on the left hand side, and then assign what you want to it on the right hand side. A little bit like you would do if you were writing math. You would have a standardized way to work out a particular problem, and you have particular formatting styles, and it's the same here. R it's less strict in how you write the code than in other languages. So for example, in Python, there is actually something called PEP8, PEP8, and it's actually a style guide which tells you exactly how your code should be written. And when you get to an intermediate to advanced level, and you're working with people who are very experienced, or you're submitting your code for review, if you're not meeting the PEP 8 style, then people will probably complain to you that your code isn't being written correctly. Talking about code style, it's probably also important for me to identify at this point that a good motto is that you would expect your code to be at least half text and comments, if not more. And that's because if you just write literally the mathematical operations or the functions, if you have to come back to it in 4 months' time, which you inevitably will have to, you probably will have forgotten what's happening. And that's why it's really important that you have proper documentation to actually demonstrate your code. So let me just give you an example. So this is a Python library which I've written. And if we just go in here into the code, all of this is just explanation. So this is executable here, these 2 lines, and then all of this here is literally explaining what this function does. Now, I don't want to scare you off because we're not writing anything this complicated at all in this module, but I'm just emphasizing that there's 2 lines of code, and then there's over 20 probably where we're actually just saying what it all does. And this is also very good practice if other people are going to be looking at your code, because you might share a script, you might put the code online. Increasingly, science is meant to be open and available and reproducible. And as a consequence, people will probably pick up work that you've done if you were to publish a paper. And therefore, you want to make it so that they are able to understand what's going on. I was out in Silicon Valley at Facebook about a year ago, and they have these fantastic posters on the wall in the headquarters, and a lot of them kind of coding related. And one of them was, if the documentation is wrong, then assume the code is wrong. Because obviously, maybe the programmer's not put enough time and effort into making sure that documentation is up to date. Well, then maybe there's all sorts of other errors riddled throughout the code base, and this is obviously really concerning. So I think for good development practices and for good methodological practices, you really want to make sure that you're on top of this. So here we've got lots of explanation about what's going on in the code, and I think that that's a really good thing. Okay, so we've done most of this. You can see here that we're able to specify that x basically is going to be a collection of values between 1 and 20. So here we've created a collection of values, all integers, so whole numbers, between 1 to 20. And actually, if we put a semicolon, then in the same line we're able to assign these values to x, so we don't have to write all of these numbers out, and then it also prints x. So you can see here what's happening, where essentially we get the full numbers that we assigned based on this particular piece of code. So you can see here there are notes which allow you to follow this through if you're not able to explicitly see what the code is doing here. I would encourage you all to both read and play with the code in order to understand what's going on. So I hope that you'll be able to run it and interrogate both in the console here and in the global environment, and read it in tandem with the text. So functions, we can also specify these. So a function can be just thought of as a group of commands that can be executed with just one specific command. So for example here, we're just specifying the square root of 25, which is producing 5. But you could have your own user-defined function that had lots of different types of mathematical processes within it. And you would only have to call it once, and it would produce the answer for you. And this is a fundamental tool which underpins pretty much all of the software which we use. So the software on this program, the software which is running on our smartphone. So this is important. We're not going to be writing too many functions within this this class. In fact, we will rarely be writing our own, but we will be using functions which other people have written, specifically the packages that we're able to install into R. So this is a native function here. It comes within the R framework. But if there's more specific functions that you want to use, maybe it's a spatial library and it does some specific spatial processing, we would have to import that and then run that specific function. But it means that we don't have to write out the code each time, and that's the benefit of it. So we can have a repeated call for a single set of functions which can be tested. We can guarantee that we know that that's producing the right result that it should be. Okay. Data organization. So here we're just demonstrating how you create a vector. So a vector is a one-dimensional data structure which holds a set of values. So they could be numeric, as they are here. So let's see what Z prints as. There we go. So we basically store these numbers as a vector and print it. But they could also be strings, so they could be letters, or it could be a mixture of letters and numbers. It doesn't really matter. It's more just about the data structure. And if you're confused by what a vector is, just think of it in terms of, in the previous presentation, we said we have a column for a variable, and we have some values. So we have x, and then we have a set of 3 values here. And this is essentially a vector. So it's when I say a 2-dimensional data structure, I mean that it has one column and it has a certain number of values. So a 1-dimensional data structure would just be a single value, okay, like this. And a 2-dimensional data structure would be a single column or a single variable with multiple values. And then you could have a matrix as well, which is like a data frame, which I mentioned before in the previous case. And this is a 3-dimensional. Sorry, it's not 3-dimensional, it's also 2-dimensional. So anyway, within this, we would refer to this as either a group of data or a data frame or a data set, it could be. But essentially, these are fairly common data structures that we'll be using as we move forward. So there are lots of different ways for us to organize and enter our data. So for example, the scan function here, if you look at the console, the scan then allows us to enter values into this specific data structure. So if we type 20 and enter, that's the first value, 30, that's the second value, and 40, that's the third value, and then we finish by pressing enter, and then we print B, we're able to obtain those numbers that we entered into this initial list. And you can see it also up here in the global environment. So that's another way. We can perform math on these different vectors, for example, or lists. So if we have a vector which is essentially 1 to 5, as you can see here, and we're then able to multiply all of the values in that vector by 2. And you can see here that 1 comes out as 2, 2 comes out as 4, etc., etc. And this means that we're able to do very easy and swift processing on a large amount of data at once. hence why computers are so much more efficient than doing manual operations. So here we just emphasize the fact, I emphasize the fact that vectors can be operated on with other vectors, but we always have this issue of needing the vectors to be the same length. So here W is 5 values long, and we're able to add V that we specified above and W, and essentially when we add them together, it's adding the first value of each of the vectors together. So we can see 11 down here from 1 and 10, and then we can see 22, which is the summation of 2 here, and 20, and so on and so forth. So this can help you understand how you can do vector multiplication or addition, or whatever you desire, whatever functions you have available that you might need to carry out. Lists. So you can specify lists, which are essentially a collection of objects, and they don't always have to be the same data type. So here we're specifying a list with multiple different variables and with multiple different values. So you can see that the list contains a male name, a female name, male age, and a female age. And that provides us with the ability to have multiple different data types present at once. So here we go, we can see this within the environment. And we're able to then index into that part of that list. So if we type a 2 in the list, we're able to basically grab the value that's listed within the second index point within the list. So if you look here at the list structure where my mouse is, you can see Steve, Sue, and then the 2 ages. Imagine this is numbered 1, 2, 3, 4. So by entering 2 here, we're able to obtain Sue, because that's the item that's in the second holder of the list. So we could change that to item 1, which would be Steve, or we could change it to item 4, which would be the number 39, so for her age. So that's how you start to index into lists. So we mentioned before about data frames. Data frames are a collection of objects, essentially, usually vectors. So if we specify x here as one vector of 10, 20, 30, 40, 50, and then we specify another vector here, y, which currently is only made up of 4 individual items, and then we basically try to make a data frame from them, we're going to get an error. Now, why is that? Well, that's because, as I mentioned before, if you're going to do operations on vectors, then you need those data structures to be the same length. So you can see here we have 5 objects in X, but then we only have 4 objects in Y. So let's just add in a 5th in Y. There we go. Now the code runs. So essentially what we're doing here is, this is a function data frame, and what it's doing is it's saying create a variable named numbers and allocate it the values which are in X. And then the same here, create a variable named letters and allocate it the strings, so that the characters within Y. And then when we add them together, essentially, we obtain the data frame, which you can see here. So we have the 2 variables which we mentioned, numbers and letters, and it contains all of those values or characters. And then on the left-hand side here, you can see what is essentially the index. So this is an identifier which is used within the program to control how the data is structured. In theory, you don't need to worry too much about the index value within R. You might do if you move on to other programs, but R does most of this for you behind the scenes, so you don't need to think too much about it. But just think of this as an ID which the program is using to control for the merging and the processing of data as you carry out operations. So we're also able to add more types of data. So here we have the data frame function again. So we've got y and then xy together, which means that we're able to add 2 or more items. Anyway, moving on. Here we can see that there are ways for us to index into this individual data frame. So as data frames have multiple dimensions, as I mentioned before, if you just select the first dimension, so xy1 here, what you're actually capturing is the vertical dimension of the first column, which is why we're getting the numbers printed here. But if you actually you then enter the index 2, you'll be collecting the second variable. And if you use the dollar operator and then select the variable, you're able to obtain all of the information that was in that particular variable. So this is actually really useful. So this is basically, you've imported some data. How do you grab the data that you want? And this is a processing technique that we use very, very often. So once you've actually got this data here, we're just printing it to the console. But you are obviously able to allocate it to your own variable names again. So we could call it var1 or var2. var1 or var2. And therefore we're able to create our own data structures. Yes, here we go. So var1 demonstrates that we've got the variable 1 just here. I'm not sure why this isn't creating a variable 2. Oh, it is. It's down here. It's because it's a factor. So essentially, it's not keeping it as a data frame. That's interesting. I didn't think it was going to do that. There we go. So why don't I use that as an example? So you see here we're able to index these columns out into new variables, as you're able to demonstrate here. And that's really useful. Okay, so far we've just worked on the vertical dimension of the data. So we have the data frame. Let's have a look at it again. Here we go, we have the data frame, and all we've done is we've extracted a single variable out of that data frame at one time. But you may want to, say, access an individual value or extract a sequence of values within that variable. And you're actually able to do this by using these indexing numbers here. So what we're saying is from the first column, select the second element. So for xy here, we're getting a. So I'm sorry, that was the wrong way around. Actually, 1 here is referring to the first row, and 2 is referring to the second column. So that's why we ended up with A here. Can you see that? It's probably worth you running this code in your own machine and understanding the implications of actually accessing these values. I personally, for exactly this reason that I just showed, I don't really like using this type of indexing method, because if you change the structure of the data frame, or if you get the indexing wrong, just like I did there, and then you can select the wrong number, and that's obviously not good at all. So there are better ways to index that type of information, so you can be more explicit about which values you want, maybe by using a column name instead rather than the column number. And that means you always grab the correct column, even if it's moved to a different location in the data frame. And actually, this is one reason why the index can be important, because I mentioned to you before about these numbers on the left hand side here, 1, 2, 3, 4, 5, which is the index, which are controls in order to ensure that the data doesn't get jumbled. Well, actually, you can specify what that index is. So you could say that if we had a data set of all of our characteristics and our names were in there, you could have the index as our names, and then all of the columns that went across would be our attributes. I don't know, height or hair color, whatever. But the key point is that you could specify the name of the individual, and that would get the row information, and you could specify the column name, and that way you could specifically get elements, so individual items of information, individual values that you want. And that would be a far better way to write the script, so that then you don't end up with indexing errors, as you can potentially get by just using these numerical ways to obtain individual data values. So the first one here, as I mentioned before, we got A, and in this one here, we get 30. Why do we get 30? Well, we're specifying the third row in the first column, so we end up with 30 here. Okay, great. So that's given you a bit of an overview of the different operators that we use, so the pound sign to comment out, and also the use of the dollar sign as well to access variables, and also how to assign number processing functions that you're using to other variables. But now we're going to look at actual data and how you access data sets. Now, we're not going to use it too much here, but there are actually a very large number of data sets which are built into R. So I've just run this piece of code here, data. And what this is doing is it's saying go into the internal memory of R and show us all of the data sets that are actually available to us. And you can see there's quite a lot in here. This one here, Iris, which is Edgar Anderson's Iris data. I'm pretty sure that's the data which I showed you before in the previous lecture. So it was the petal length and the petal width. And remember, we looked at how there was positive correlation between these two measures of length and width for certain plant species. And that's one which comes up time and time again. So you'll see a lot of examples on Stack Overflow of where people have showed how this particular thing works, which maybe wasn't working for someone, and they'll use one of the inbuilt data sets, very much like the Iris data set. Okay, so they're all the inbuilt data sets, and we're able to load one. So let's load BOD, and we can get the description for this. So the description is that essentially the BOD data, BOD data, is the biochemical oxygen demand, and it has 6 rows and 2 columns, and it's showing the evaluation of water quality over time. So this is each day period here, and this demand variable here is actually the biochemical oxygen demand in milligrams per litre. So this information is all listed within the actual help within R for the data set, and that's one of the benefits. So you can use these internal data sets and have all of the important parts of that data set explained to you from the help menu, and you can practice how you might visualize and hypothesize about the workings of the phenomenon question that the data is representing. Okay, so that shows you how to access the help menu for the inbuilt data sets. We're also able to subset some of these variables. So as we've seen already, when you've got columns, you're able to use the $sign to actually access them. So here we just basically went into the biochemical oxygen demand data set, and what we did was we specified that we want to grab the data from the horizontal dimension here, and just grab all of the time information for those 7 days. And currently it's just printed them down here to the console, but you could just create a new variable if you would like, and the time information is basically allocated here from the data frame to the time, and it shows up with those values in the global environment component here. So this is essentially what we do here for each of the different metrics, and we're able to print them simultaneously to the console. So that's a bit repetitive, so it's good though for you to understand what these different functions do, and it's definitely trial and error, and definitely helps to repeat some of these functions. So maybe if you play with this data set the first time and it doesn't make sense, then it's definitely worth recapping and having another go, maybe watching the video again, and maybe Googling for other YouTube videos if you're stuck on any parts. And that type of learning experience should help you understand the code over time. We can also take vectors and create a data frame from this. So here, when we basically allocated these variables, you see they just ended up within this values section here. They're not actually a proper data frame. Well, we're able to combine them together as we've done previously to create a new data frame. So here's the new BOD data set. It's got new column names, which we named before, but with all of the same information. So this is what can be termed data munging in coding and scientific computing circles. What that basically means, data munging, is the process of manipulating data. So for example, you may actually only spend 10 to 20% of your time doing the complicated analysis bit, but actually potentially up to 80% of your time could be spent just manipulating the data, getting the data in the right form, and that can take a long time because some of the programs need you to input the data in a specific way, particularly if you remember the charts that we went over earlier in the lecture, where we had up to 4 or 5 dimensions of data. They really do require quite a bit of work to get the data in the right shape, for you to then place that into the correct R code to create the visualization. Okay, so moving on, how do we actually import our own data? So the internal data sets that we just covered, well, they're all very nice and good, but the reality is that they're just there to play with. They're not actually going to be what we do real science with, and that's why we need to import the data that we've collected ourselves. So here we can read from an external file, essentially by using the read.csv function. It's important to make sure that your working directory is set, and I'm not sure that we did it fully earlier on, and that's partly because the code is listed down here. But let's do that now. So just before we begin, you can access the read.csv function. So here I've just typed help and the read.csv, and basically this single line here has produced this documentation, which describes that the function basically is able to import data in a table format to create a data frame. And basically the lines correspond with the cases or the observations based on the definition which we used before, and then the variables essentially to the fields, the vertical columns within the data. So how do we do that? Well, first we need to set the current folder. So this piece of code here doesn't look very nice, but essentially what it's doing is it's saying find the current folder that I am in. And what that's doing is saying, well, you are on the C drive, you are in users, and you are Edward, and you're in your Dropbox, and you're in teaching, and you're in GGS300 quantitative methods for fall 2020, week 1, the first lab. So that's what that code produces, and it gives us the folder path. And this is a really nice way to not have to explicitly state which folder you're in. So if I give you the code and I've explicitly written, as I used to do when I first started, the folder path, then that means that when it goes onto your computer, the code isn't going to work because it's going to be a different folder path on your computer. So it's not going to be able to find the data or any of the information that you need to run. So the beauty of this is that it's agnostic to which computer it's on. It just says, well, where's the script? What's the file path for that script? And then as long as everything is in the same folder as the script, then this will just work essentially for importing the data, because the folder here is passed to this function, file.path, which just combines the folder with the file name here, precip.csv. That then provides the full path to access the data which we want to load. So here we go. This is the folder which I'm in, and this is the precip data. Here you go, you can see the year, so it's rainfall. It's a historical time series for Washington DC and Baltimore, and actually the rainfall, the annual rainfall, is in inches. So that's what it looks like in a spreadsheet. But once we enter this, let me just clear the environment so that you can see what's happening fresh. And I run it. Sorry, my bad. So I need to collect the folder name first, so it's in the memory, and then I need to read the CSV. There we go. Now we've imported that data as the data frame rain, and you'll see that when we open it up by clicking on it, we have the year here vertically, and we have also the amount of rain for DC and Baltimore, just like we did in the Excel spreadsheet. Great. And we're able to print that to the console should we wish, but obviously it's in our memory here. That's the most important bit. So that's how we get data into R. And then what we want to do is we actually want to understand that data, and we actually want to plot it. So here we can understand what the plot function is. So plot is just an inbuilt R function that's just generic X versus Y plotting for plotting our objects. So this is fine to use. It's comes with a package. It's more basic than some of the other packages, but it does the job. It's maybe not as flashy, doesn't look quite as nice, but we're going to just run through it first so that you know the very basics. So we are able to take the data rain, we're able to plot. So here, if you look at plot, so we said, what is this function plot here? And then when you open up the documentation, it says this is the usage, well, plot X or Y, etc. What this basically means is you can put a variable in here for X, like rain DC. So this is saying go to the rain data frame and then get me the variable DC, which is the rain in DC. And basically it's just plotting the single variable. So this is rain here on the y-axis, and this is just the index here. So this isn't necessarily a plot that you want to put in a scientific paper. It's just saying like this is how you make the function work. The reason why it's doing that is because we didn't give it a y variable. So you saw in the usage here, it wants an x and a y. And also we can plot the year. And here it's plotted just against its index again, but it just shows us that we're able to produce an initial plot. So how do we produce something that's actually meaningful? What would be meaningful here is actually the year and the amount of rain per year plotted against it. So let's do that, and now we're providing it with an x and a y variable. And this is the type of plot that it's producing. So you can see rain here on the y-axis, and on the x-axis here we're seeing the year, so from 1950 all the way up to 2010. Generally, we don't really see much of a data pattern here. We have a bit of an outlier up here, around about 2003. But generally, there's not really much of a correlation in these data sets, in these data points. So it says here, plot always starts a new plot, and it depends upon the arguments which you give it. Obviously, we know that. Yes, and we're explaining here that it will use default values unless you actually explicitly say what you want the function to do. So it will require you to enter the data, but then a lot of the other abilities that the function has, it will just use a standard default approach if you don't enter anything specifically. So for example here, it's used the variable names as the standard axis labels, even though we didn't specify what labels we wanted. So here when we plot, we're able to change the plot type. So rather than using a scatter, what we actually do is we transform the plot type into a line graph, and it's plotting the change each year. Sorry, it's not. It's plotting against the index, and it's showing the actual rainfall in DC. Okay, so this is just an example of essentially what the function is able to do. Let's produce a more complete plot. And here we're able to actually specify the type. We're able to specify the color. We're able to specify the title of the plot, as well as what the labels are going to be for the x and y axis. And this is much more important. So we're actually able to produce a proper scientific graph here, and this will obviously be essential for your future coursework. So do look into all of the functionalities that plot provides you with. And I think here, if you look at the inbuilt help, it actually gives you, see where it says arguments here? So x and y, these are the different data variables that we need to give it. But then you're able to change the type of the plot. So P entered in the type part here produces points. L we're using now produces lines, etc., etc. So you're able to go through this and actually specify whatever you want to provide you more control over what you're producing. So let's produce a histogram. So we went over histograms in the previous lecture, and histogram shows the frequency of individual values, and this is the annual rainfall for Baltimore. And we haven't specified what level of aggregation we want to use, so what the widths are of the bins. So when I refer to bin, I mean each one of these columns is a bin, and we can specify how many values we want it to catch within each range. Here it's just allowing the function to use default parameters, and it's essentially binning, I think, every 5 individual units. So this is 30 inches, 35 inches, 40 inches, etc. And then showing the number of results that it has within each one of those bins. So we specify the number of breaks that we want here. And this time we say that we want 70 breaks essentially, which go from 0 up to 70 inches per year. And that's useful because you're able to do two things here. One, you're able to specify the bin width to a certain amount. So if you have fewer breaks, that's going to mean that you have fewer bins and more values likely per bin. But then also you're able to specify a range if you wanted to. So if you just wanted to choose values between 40 and 50, oh no, it won't actually let me do that here, unfortunately. I think that's because plot is an inbuilt function, so it doesn't give you the full range of abilities that maybe one of the more advanced packages like ggplot would allow you to do. So what it's actually saying here is your breaks have to capture all of the data which is present in the data set. I think that's why it said that you see here, breaks maybe do not span the full range of X. And what that meant was that there were values that we weren't capturing within this very narrow range. So I think what you would need to do if you just wanted to plot values between 40 and 50 is subset them first and then apply the breaks. But that's one step too far, so we're not going to do that today. Okay, so let's move on. And here we're just demonstrating that so this breaks parameter allows you to have, say, just 2 breaks, which produces 3 bins, or 4 breaks, which produces 5 bins. Here we go. This is the variable which allows us to specify the range. So if I take the parameters that I wanted to test before, I should be able to get this to work now. Yes, I can. That's great. So it does work. Let me just give you a truncated distribution. And I can explain what we're doing. There we go. So what we did was we took the data frame rain and we took the column for rainfall in Baltimore and we took the values which fell between 30 and 60 inches of rain per year. And then we said, put them into 10 individual breaks. Aggregate them into 10 individual breaks. And these are the values that we produced. So this is the plot that we produced. So here you can see between 30 and 60. Great, so I'm glad we were able to do that. So that's a defined range of X. And we're also able to be a bit more explicit about the intervals that we use. Again, I'm getting, I see. It's the same problem that we had before. So again, the breaks that we were specifying, they weren't encompassing all of the data. So we were only specifying breaks at 20 up to 60. And we have values that are larger than that. So we have values that are over 60. So it didn't like the fact that we weren't including this last observation here. So I had to expand the breaks. I think this is a good example of how you're going to need to debug your code and you're going to need to work out what's wrong. And obviously that's easier if you've got a bit of experience. But if you're just starting out, then this emphasizes why it's good to work with others or to have contacts who who may be able to help you if they're older, or maybe they already know how to use this. And if not, then there's always Stack Overflow, Google, and as a last resort, reach out to me and I'll try my best to help you. So, this is just an example of how I need to fix the data. So I think that this was put in here specifically to produce the error, and then what I do here basically is I capture that error and make it work by adding in that final bucket. Great, so that's plotting histograms. We've covered that within the lectures, and now we've covered how to actually import data here, and then to plot that data and actually produce a nice graphic. Now let's move on, and I'm just going to quickly point to two different types of plots which are maybe a little bit more advanced. So these are cumulative frequency plots. So we've got data which we've already loaded in for DC, and we're able to create a plot, essentially a cumulative absolute frequency plot, which provides us with the number of scores which fall above or below a specific value. So let me show you what that means. So I'm plotting, I'm enabling this one line here. I'm running this one line, and it's producing this graphic here. And what this essentially shows is it's sorting all of the values here. So this is these are all of the sorted rain values annually for Washington DC, between about 28 inches per year up to about 62 inches per year. So you'll recognize that range because when we were here and we looked at the maximum value in DC and then the minimum value in DC, it corresponds to this value down here at 28 and this value up here at 62. So if you look at the values on the x-axis, they correspond to those points in the range. And then here on the y-axis, what we have are all of the individual index numbers. So it's basically just a ranking. So we have in our data frame 68 observations. So you'll see here that we go from 0 all the way up to 68. And therefore we're able to understand, well, if we have approximately 70 values and we have about 35 would be the middle points, then we're able to understand how many values fall above or below that midpoint. And that's really useful. That's incredibly useful for many sectors of industry. So me just explaining it here is quite dry and theoretical. But actually, there are lots of people in the insurance industry. So if you go to New York, for example, and you go to some of those major insurance companies like AIG, American International Group, one of the main ways in which they understand risks to the economy or to households is through this type of distribution. So let me just show you. If I plot this here, what we're doing is we're converting the absolute frequency into the relative frequency. So essentially the plot that we produce here is between 0 and 1. So we just normalized the y-axis basically. All the other values are the same, but rather than there being the number here being the index value between 0 and 68, now we have a number between 0 and 1. And actually that can be thought of as a probability in some ways. That could be thought of as a percentage. And that means that we have a statistical framework to understand how likely certain events are. So going back to the insurance context, the whole insurance industry, I know insurance sounds very boring, but actually there are some very interesting parts of the insurance sector. And I would thoroughly advise any of you to at least consider going into it if you had the opportunity. Mostly as well because, I mean, some of you are physical geographers, and they do like people who have that type of physical, natural science understanding of catastrophes such as hurricanes or earthquakes. So the insurance industry works by taking premiums from you and I, households or businesses who pay a small amount of money. And when something negative happens to a small percentage of those people, the insurance company is able to pay out for the damage that's been caused. The issue, therefore, is how to understand how to price what people should pay. If you price it too high, it's too expensive, people won't buy it, or you'll be priced out of the market. If you price it too low, then when something bad happens, you might not have the money to pay out, and then your business goes bankrupt. So they use this type of understanding of extreme weather patterns to understand what the probability might be of, say, a year where there was over 50 inches of rain in DC. And this might matter because maybe when there's more than 50 inches of rain in DC annually, there's a much higher probability of extreme flooding and your house being flooded. And if that was the case, then maybe they would have to pay out a lot more of additional. They would have to pay out a lot of additional cash to people who needed their homes repaired or their businesses repaired. So this is one of the ways that they think about these types of extreme weather patterns. And even some of the models which have been developed, so they're called catastrophe models, to look at the damage that might be caused, for example, by hurricanes. They actually trade in financial markets based on the estimates which the models produce for how much damage there might be and what the probability of the damage is, and that affects the price of that particular product that can be sold, for example, in New York on the financial markets. So anyway, this is just me relating some of these techniques to how they're used in industry. And I think that that's important, because I don't want this course just to be really dry math or coding. And I think that the minute that you start to see all the wonderful applications for what we're actually doing here, then you will definitely be, inspired, hopefully, to continue working in this area. Okay, so that just gave you a little bit of an overview of the cumulative frequency plots. These are very simple, but it just gives you a bit of an understanding about how we can understand the distribution of values cumulatively. So how do we actually produce graphics? So here we have some low-level graphics commands, again using the inbuilt hist function, so it produces a histogram. And currently we've turned off the axes. We don't give it a title. We turned off the X label. So the X-axis label, there is no X-axis label. And we turned off the Y-axis label. So it is just literally the histogram. And then what we're able to do is we're actually able to give it a title. So we're able to use the title function, which just takes whatever is in the graphics window here and adds the histogram of DC precipitation. That's the chosen title that we wish to add to this particular graphic. We can also give it a color, so if we rerun that command and we've added in the col main blue function, you can change the color here. This could be red or orange. And if you want to understand what colors you can input into here, then actually you just need to R color palettes, there we go. And then this will just basically tell you all of the different color types that you could use in R. So do explore that. So we're using just a very small number of features here, but you have the ability within R to change pretty much everything within each of these plots. So you could even color all the bars differently if you wanted to. And then finally, let's just add in some X and Y labels. So here we've added in to the Y label frequency on the Y-axis. We've added in the X label on the X-axis for precipitation. And then we've, not sure why it says measures there. Let's rerun that. And then we've said that we want the column labels to be red. So you could change that to blue if you wanted. So this is just giving you a little bit of the functionality for what could be done with just this one very simple function. So how do we actually create nice looking plots? So the par option opens a graphics window and shows you all of the current settings for that window. So these are all the settings basically that I've just printed out to the console. So if you were going to produce a very complex plot, you could have a function which just loads in a load of preferences which you have for how you want the graphics plot to be set up. So now we're just doing something very simple. So essentially we're just importing a lot of the default settings. And we're basically telling the graphics plot here that we would like to have multiple rows. So we're going to have one column and 2 rows. And then we're going to put our graphics into that graphical plot. So let's insert the first one, which is the histogram of rain in DC. And let's put the second one in, which is the histogram of rain in Baltimore. And there we have our finished plot. So once we have that plot, what do we do then to export it? Because you're going to need to put this into your scientific paper or share it with your collaborators. And over here in the graphics plot, you can see that we have the ability to export it either as an image, so a PNG, for example, portable network graphics. I think that's what PNG stands for, or a PDF as well. Or you could just copy it to the clipboard. I think if you just copy it like this, you're even just able to paste it into Word. Yeah, so you can just paste it in that way. I'm wondering if when you paste it, what you paste it as, oh, you can only paste it as a device-independent image. Okay, that's fine. Well, I think that that looks reasonably good quality, so I think that's fine. Yeah, so there's multiple different ways that you can export. If you do that using one of these functions here, I think you can actually give it a proper name. Yeah, you can. So let's just say it's rain panel, and then you can save it. And I'm not sure where that's saved to. Let's see if we can do that again. Directory, that's what we need. We need to set the directory to, yeah, the folder that we're using. So let's try that again, rain panel, and try and save that. And here we go. Now we have our exported panel of histograms. And I think that's pretty nice. You know, I showed you before some of the graphics which I've produced in some of the papers that I've written, and you'll notice that you can definitely portray a lot more information once you start to get into producing these panel plots. And a panel plot is where you basically have more than one graph in an individual image. So this gives you a good start to do that. Now, we exported that manually, but you can actually export it. You can automate the exporting process in R, and I'm going to show you how to do that in a second. But just before we get onto that, I just want to show you a couple of other functions. So you can view objects that are in the memory. So here, what we're doing, if I just close this, is I'm saying, please can you list ls, open bracket, close brackets, exactly what's in the memory currently. And what we have is the folder value, so that was the path for where we are currently operating. And then we have these two objects, these two data frames, old par and rain. just here. So that's handy, we're able to see exactly what's there. But we're also able to remove objects from the memory. And actually, you've seen me do this as we go through. So I haven't written it in the syntax as here. I've done it manually, but I'm just going to show you can do it with both. So here, on this line 256, I can remove rain, the data frame that we were using. So let's do that. There we go. And did you see it removed from the environment? It's the same as me essentially doing this, which is just to remove the objects from the memory of the computer. So I click yes, and that emptied the whole memory. So you can do it in whichever way you want to. So let me just rerun all that code. Then we've got rain loaded in again. When we're down here, let's remove bod, my list, new bod, old par, var1, var2, xy. Let's do that. And that did remove all of those variables, which was good. I was surprised that it removed rain though. So I'm going to get rid of this. I wasn't sure why rain removed. I'm going to go back through and load rain in again because we're going to need it. So we go up here to where we're able to access the folder. And then we use the function which I mentioned before, rain.read.csv, to get the precipitation information and read it in as rain, which we've got here. So we've completed how you see the objects in memory and remove objects from the memory. And now I would like us to just quickly focus on ggplot2. So in the previous lecture, I spoke about Hadley Wickham's book and all of the fantastic software that he's produced. You might even have looked at his Wikipedia page, or maybe some of the websites that he's contributed packages to. And I mentioned that tidyverse is the name for the software environment, the package of software that he's essentially produced. So if you type tidyverse in here, then you can see all of these different packages. So this is graphical visualization, which we're going to use now. This is data manipulation. This is to tidy data up. And there are lots of different types of packages that make up the tidyverse that is so used so widely these days in data science, in spatial data analytics, so people doing geographical data science, for example. So we need to install these packages. Now I'm not going to install tidyverse here because it can be quite large, so for now I just want to install one specific package, which is ggplot2. And to do that, if it's not already installed on your computer, then you will need to run this code here, install.packages, and then open brackets, and then type ggplot2, and it needs to be in apostrophes or quotes. And let me run it here. It's already installed on my machine, but it probably won't be installed on your machine. And what it's doing is it's going to the CRAN, which is basically where all of the R packages are stored on the server. So let's see what CRAN stands for. The Comprehensive Archive Network. And this is basically a group of servers around the world that has all of this code on, which allows you to just pull down the packages that you want. So here when we install, it loads it all into our computer, and this is what we're really looking for. We want it to basically say ggplot2 is successfully unpackaged. Okay, and then once it's unpackaged, every time you open up your code, you will need to bring the code for that package from your hard drive into the current environment so that the functions that we specify can be accessed. So you need to type and then enter library ggplot2 in order to access it. So it loaded that in. Ignore the error messages. You can get quite a few in R, but in this case, it's just complaining about the fact that maybe it doesn't have all of the packages that it needs. But it's fine in this instance. So we'll be able to run the code that we want. So that imports the visualization package, and it allows us to start getting plotting. And I just want to produce a very simple histogram. This time we're going to use the ggplot function. We're going to call the rain data frame that I just re-imported a second ago. We're going to say that on the x-axis we want DC, so it's the annual rainfall for Washington DC, and AES means aesthetic. So basically what that means here is that we want to graphically illustrate this one variable which we're specifying, and the AES allows you to involve lots of different variables and also specify a whole load of color parameters or style parameters, so color, shape, size, the type of lines that you're using. It's endless. So that's important to know. And then as this specifies the variables and the data, this second command, which is tagged together by a plus, just specifies that the geom, which stands for geometry, here we'll be using is a histogram, and that the bin width, which we're going to use, I mentioned bins before, is 5. So let's plot this, and what we get is our first GG plot, and we're able to show the precipitation for DC. And we've binned these based on a width of 5 units, as you can see here. And it looks fairly unimpressive at the moment, and that's because I just pulled out these very two simple blocks of code. But what we really want to do is we want to provide a title and a subtitle and start to label all the axes. And that's why just down here, what I've done is I've produced a little bit of code which then just adds on the axis labels for the y and the x-axis. So you can see here they're labeled very straightforwardly, x and y. And also I've added a title as well as a subtitle. So just to give you a bit of a flavour for the ability that you've got to really provide a lot of information and change a lot of the styles within your plotting environment. Here you can see we have the distribution of annual rainfall and the subtitle stating that it's data specifically for DC between 1950 and 2017. So when we run this here, we are basically assigning this plot to this variable DC, and it's adding it into the memory, and it's got quite a lot of complicated information associated with it, which you don't need to worry about. All you need to know is that it's been assigned to this variable name, and now what we're going to do is we're going to automate the export of this individual image. So what I first do is I create a file path. Now this is the folder variable that we used before, so this is the path to where the code is, and then this is a name for the individual file. Here it's a PNG, so a portable network graphic image, and what file path does is it stitches together this first part of the path which we obtained from before, and then the file name. So if I actually just type path and execute it, you'll see that it provides me with a string because it's in quotes. So it's a list of characters. It's a variable with characters in which has the specific path for where we want to write the image to, and it also specifies what type of image we want it to be. You see it says PNG, and it uses that path essentially in the GGSave function here to say, write the information that I'm going to give you in a minute out to this path, and I want to specify the width and the height, which I do here in inches, and I also want to specify the quality, so the number of DPI. I'm not sure what DPI stands for. Let's look at that. Dots per inch. That makes sense. So specify the number of dots per inch. So 600 DPI would be obviously a lot higher, twice as high resolution as the 300 dots per inch here. So once we execute this, it sets up the file path, it sets up the image that we want to create, and at the moment that's created a PNG file. So let me just delete that and rerun this again so you can see what it's doing. It's creating the file here, and it's writing the information into it. So here we go. There we go. So now it's created the PNG. It's written all of that information in, and we're able to export it, and there's our first graphic. So it's very simple, but it starts to give you a bit of a flavor for how to use the syntax to actually take advantage of the power of R, and in particular ggplot. So that's the end of this this lab. This has been the first week, so essentially we've taken a bit of an introductory approach. I appreciate we've covered quite a bit of ground now, especially in this session. It's quite a long one, but I think that it's worthwhile spending time doing this introduction so that you all know how to use the software properly. So I'm going to thank you for your time. I don't think we don't have a lab homework this week. The lab homeworks are going to start next week. So this week, what I'd like you to do is to read the information that's been specified in the course syllabus. So that's essentially chapter 1 in the textbook, which I mentioned before, which is here. And I would like you to run all of the code which I've specified here, and also to take a look at the links which I've provided within the code. So that's about it from me. Thank you very much, and I look forward to seeing you all soon. Thank you.